Allows lower frequencies to.
Allows low frequencies to go through. So a low pass filter on top of this diagram, and let me pick a different color, is going to look like this. There's a low pass filter that's been applied to that. Now, as a result of that particular low pass filter, is that low pass filter going to block out any of that signal that I have shown?
No.
Not really. I mean, we certainly are going to have the 9 kilohertz up here, 11, and of course it is going to go on basically through to infinity, but as you can see, the contribution of the higher frequencies is pretty small. So by cutting out those high frequencies, we're really not going to have too much of an effect. But what happens if I decide to change the cutoff frequency of my filter and make my filter, instead of going out that far, maybe I set up a filter that goes like this. It's going to start to cut off part of that square wave. In fact, think about this. Is it conceivable that if I applied the right filter to these, that I could get this?
Yeah.
Yes. Same fundamental frequency amplitude, but this is lower, this is lower, this is lower. So if I were to filter a square wave with a low pass filter, what would I get?
Triangle filter?
I might get a triangle wave. So I'm going to put this through a low pass filter, my square wave, through a low pass filter, and out of that is going to come what? A triangle. Because I've cut off some of those, what are these called?
Frequencies.
Harmonics. I've cut off some of my harmonics. And if I were to filter that even more aggressively, to the point where I did something like this, with another low pass filter, now I'm showing it in blue, I'll get a sine wave.
Because you only get one signal.
Because I'm only getting, if I filter it too close and too tightly, I'm going to lose all my harmonics, and the harmonics is what gives the waveform its shape. With no harmonics, what do you have?
Just regular sine wave.
You have a sine wave. You have the fundamental building block of all waveforms, but you've cut out all the harmonics, haven't you? You've kind of taken a color picture and turned it into black and white. There's not much left. So if I filter a square wave, I'm going to lose the integrity of that waveform. Okay? Well, yeah, I'm going to go, as I filter it more aggressively and decrease the cutoff frequency of that filter, I'm going to cut off more and more of the harmonics. And the waveform is going to change as it's filtered from that square wave. It'll go through, it'll start to round off on the corners. You'll get to a triangle wave. Then once you get to the triangle wave and you filter that some more, it starts to flatten off or round off the tops. The higher frequencies are what give you the angles of the waveform. The lower frequencies are what give you the curves. That's probably another way to look at it. So when I cut off all the high frequencies, I'm losing all of the sharp edges and angles. And I'm going to end up with nothing but the original curvy sine wave. Okay? Now, why would I possibly be interested in this? Why is that important to us?
Different things run on different frequencies.
Well, sure, different things run on different frequencies, but shouldn't they be able to run on a sine wave? Why do I need to worry about that? What's the difference between having a sine wave and a square wave? Because really, we don't really care too much about this. This is just kind of intermediate. But what's the difference between a square wave and a sine wave?
One has more dramatic. One dramatic drops, right? It drops more dramatically.
It's more integrity.
I'm looking in through my binoculars far into the distant future. As a matter of fact, about 5 weeks from
At a
now.
higher frequency, suddenly at a lower frequency.
What happens in 5 weeks?
Yeah.
No, what's after the radio? There's only 4 weeks or 5 weeks
Yeah,
left in the term.
Digital.
Digital. Digital. What is digital made of? Ones and zeros, right?
Binary.
Or is one somebody that came in to apply for a job one day said digital is a science of ones and twos. Needless to say, did not get hired. Okay? But in the digital world, we have zeros and ones, which are a square wave. Highs and lows, ones and zeros, trues, falses, yeses and nos.
White and blacks.
Right? So if I'm sending digital information from one place to another, I have to make sure that what doesn't happen?
Starts to round off.
I have to make sure it doesn't round off. Because once it starts to round off, then I'm not really sure whether I have a 0 or a 1, am I?
You get distortion, right?
I'll get digital distortion, or what normally happens is I get data errors. Okay, I'll get errors in the data. Because if these things start to get too rounded off, what ends up happening?
The sine wave.
You'll end up with a sine wave. And sine waves are not finite zeros and ones. There's really no gray areas in between. There's either a 0 or a 1. There's nothing in between. With a sine wave, there's only 2 small spots that are actually the bottom and the top. Okay? So we run into situations with the integrity of the data. And granted, I'm talking about next term, but not really, because filtering is part of this term. But you know, it's kind of a waste of time to explain stuff like this if you can't put it into some type of context and say, why the hell is it important? Who cares? Well, this is why it's important. It's important because if you go online and you look up the USB standard for the universal serial bus that we use in back of here,
Okay.
there's a limit as to how long the cable can be. For Cat 5, there's a limit for how long the cable can be. Even for the old COM ports, RS-232 COM ports, all that stuff, there's a limit as to how long that cable can be. Why?
Because there's ZB logs? Yeah, because it's a wire.
Because of the lies you were told in first term, right? Because of the lies you were told in first term. Let's show that again, and we'll see that we've now come around the circle, and we're right at that place that we talked about. Was that, what, 2 or 3 weeks ago that we did that? We drew up what wire looks like, remember?
Mm-hmm.
And we said that wire looks something like this. Didn't we? What is that?
Same minute. Wire.
Well, I can identify the individual parts, and I would assume that you should know those, but what is this circuit? Looking at what you've already learned about filtering.
It's a high band.
Right here, X sub L is equal to what? 2 pi FL?
Right.
X sub C is equal to 1 over 2 pi FC, right? As the frequency goes up, what happens? X sub L goes up. Here, as the frequency goes up, X sub C comes down. So, is it a filter?
Yeah.
Yeah.
What kind? Low pass filter. Which means if I put a square wave in here and I filter that square wave, what might I get here?
Triangle.
I might, looking at the same drawing that we looked at earlier, get a triangle wave there. And if I filter it some more, what am I going to end up with, Mr. Harrison? I'm going to end up with a sine wave. Right? Bye-bye data, gone. We lost all our ones and zeros. Why? Because we had too long a piece of wire. We exceeded the length of the wire that would allow us to maintain the integrity of the original data or the original signal. Okay? That's why these different connectivity options that you have, USB, COM ports, printer ports, Cat5, Cat6, all of those different, we call them protocols, but all of the different systems that we have for communication between digital devices, they have limits to them. And the limits are based on the copper that we are using to get the information from one place to another. What's the resistance come from in the wire? Why do we have resistance in wire? I thought wire is just a piece of copper.
Well, copper has its own resistance.
Copper isn't a perfect conductor, is it?
Plus, it's probably have impurities in it.
Diameter's going.
Sure, there's going to be impurities, the diameter of the wire versus how much current you're trying to jam through it. So, of course, wire has resistance. Just the fact that it's made in an environment that has gravity is going to mean that it has resistance. Because the different molecules of different atomic weights are going to settle out in different areas as the wire is manufactured. If you want to make wire in outer space, it has less resistance. Because it's, I don't know what the term is, homogeneous. Homogenized. It's all the same all the way through that piece of wire. That's a good word, isn't it? Homogenized. Reminds me of milk. What about inductance? Is there inductance in wire?
Absolutely.
Yep.
Absolutely. And capacitance? Did we talk about capacitance in a wire?
Yeah.
Where does that come from?
Each one.
Well, you normally have two wires in a system, don't you? You have voltage, and that voltage has something that has, it doesn't do me any good to have 9 volts unless I could say 9 volts compared to what? Right? With the, you know, at the risk of sounding like a dope addict, how high am I now? Well, unless I know what I'm measuring myself against, I couldn't possibly tell you. Could I? I'm standing on the ground, but, well, we're probably 300 feet above sea level here, so I'm 300 feet high right now, measured against sea level. So in order to determine where we are, we have to have a reference. Well, the reference for this is ground. So when you have a wire and a ground, like we said before, you're going to have a ground here, and you're going to have a piece of wire with an insulation between it to ground. What's a cap?
2 plates.
2 plates of insulation between them.
Wire, insulation, between, and ground. Equals, same thing.
Makes sense.
So guess what? There's capacitors in there. There's capacitance in your system, there's inductance in your system, and there is resistance in your system, which ultimately gives us a low pass filter.
So you're saying is any wire we use is going to act like a low pass?
Any wire, and all wire does filtering. I think we made a couple of statements when I came in here last time, and one of them that says that all circuits and devices are filters. Did we say that? You remember that? Do you remember us saying that?